So a factory is producing bottles of perfume. The bottles have a mean volume of 51 milliliters, and historical data shows that they're normally distributed with a standard deviation of 1 milliliter. Some tweaks have been performed on the filling machine, and the manager wants to know whether the mean volume of the bottles has subsequently changed. A sample of 25 bottles are randomly selected, and their volume is measured to have a mean of 50.376 milliliters. We need to test whether the volume in the bottles has changed, and we're going to be using a level of significance of 5% for that test. Alright, so that's a lot of information to take in. So the first thing I'm going to do is kind of put it all down on paper. So we have a population, which is going to be all the bottles of perfume in this factory. So what we're told is that they have a mean volume of 51. So that's going to be the mu for the population. And it has a standard deviation of 1 milliliter. So that's going to be sigma. So what we're looking at is a sample of bottles from that population that have been randomly selected. And we're told that we have 25 bottles in that sample. And their volume has been measured to have a mean of 50.376. So that's going to be X bar for the sample, so the mean of the sample. And of course, if you wanted to, you could always work out that mean value using these data points that you've been given. But of course, the question has kind of shortcut that for us and already worked out the average. All right, so first thing we need to figure out is our null hypothesis and our alternative hypothesis. So HO, that's going to be the hypothesis of no change. So if our population has a mean of 51, that's going to be our null hypothesis, okay, that the mean doesn't change, it's still the same. So the alternative, which is H1, all right, that's going to be the hypothesis of change. So what we're looking at is whether the mean volume of the bottles has subsequently changed. So when we say changed, that means that the mean volume could have gone up or it could have gone down. So when we write it out this time, what we're going to say is just that the mean does not equal 51, which means again, it could go up or it could go down. Alright, so the next thing to figure out is our level of significance and using that to write out what our decision criteria are. So we have two approaches that we can use. One is the p-value approach and the other is the critical value approach. Now I prefer the p-value one, just for personal reasons. So that's the one I'm going to go with here. But of course the critical value approach gives you the same result. So if we're using p-value approach, so alpha, we've been told that we're using a level of significance of 5%. So that's what alpha is going to be equal to. And what we know is that if the p-value works out to be less than the alpha value, that means that we are going to reject HO, our null hypothesis. If the opposite happens, so the p-value is greater than our alpha value, then we accept HO. Alright, so now we just need to go figure out what the p-value actually is. So let's draw out our distribution X bar, which is the sample means. And of course we know that if our population is normal, which we were told it was, that means that X bar, that distribution is normal as well. So we can figure out the mean and standard deviation. Sorry, that's the standard deviation, mean. So mean's the easy one. We know that the mean of X bar is equal to the mean of the population, and we have that as being 51 milliliters. Just leave it as 51. And the standard deviation, we have our equation for that, which is sigma on square root n. So sigma is the standard deviation of the population, and we were given that as 1. N is the number in our sample, which is 25 bottles. So 1 on square root 25, which becomes 1 on 5, or 0.2. So let's draw our diagram. It's normally distributed. The mean here is 51. And I'll mark over here X bar's standard deviation was 0.2. Alright, so our point of interest on this is that we have a sample which is 50.376. So that's going to be, say, here somewhere. Alright, so what we're looking for when we test this hypothesis that the alternative is that mu is not equal to 51, we want to look at getting this result or something more extreme. But since this time we don't really care whether the more extreme is larger or smaller, what we're going to have is a two-tailed test. Okay, so we need to figure out the probability of getting a mean of 50.376 or less, as well as we're going to have the probability of getting some point here or more. Okay, again, that's because we're looking at whether the volume of the bottles has changed, so it got bigger or smaller, not one way, so not whether the volume of the bottles has got smaller. Okay, and that's where the one-tail versus two-tail test comes in. So we're going to be doing a two-tail one. So what we need to do is figure out the Z values that everything corresponds to, and that's because we already know the standard deviation, so a Z test is what we're going to perform. If we didn't know what this standard deviation was, then we would look at a different test, which will come up in future videos. So when we convert, we know the mean goes to 0, so that's easy. We can figure out what this one goes to. So 50.376, we have our equation to convert. So substituting in, our X bar that we're interested in is 50.376, mu is 51, and this here is 0.2. So this works to be 3.12 and it's negative. Alright, that makes sense because it's below the mean. Alright, so it has to be less than 0. Now the trick here is that we're looking at this result or more extreme on the other side as well. And because our distribution is symmetric, if this is negative 3.12, then the other side is going to be positive 3.12. So to get out our p-value, all we need to do is figure out the area in both of these sections. So we can write out our statement. So p-value is going to be the probability that X bar is less than 50.376. And because we know that it's symmetric again, so whatever this probability is, it's going to be equal to that part. So I can just write this as 2 times that probability. Now we want to swap this over to the Z version because that's what we can look up in tables. So we can say this is going to be equal to 2 times the probability that Z is less than, negative 3.12. Alright, so now we just need to put this in a form we can look up in the tables. So 2 times, so the probability of this section in here that we're looking at can also be calculated as 0.5 minus the probability from negative 3.12 to 0. Okay, again because half of this has an area of 0.5. And then we know again it's symmetric, so we can write this as being the flipped version, so 0 to Z to positive 3.12. And of course, that's kind of this section in here now. Alright, so let's go and look this up in a table. It's 3.12 that we're interested in. So looking down here, this is 3.1, and we want the second decimal to be a 2. So that's this value in here, 0.4991. Alright, so this is going to be 2 times 0.0009 or 0.0018. Okay, so that's our p-value in decimal form. Remember, we can always change it over to percentage form by multiplying by 100, and what we end up with is a 0.18% chance of this happening. So that's an incredibly small chance. Again, remember that the p-value represents the probability of making a type 1 error, so a false positive. So the final thing to do now is just to figure out where that sits in terms of our criteria. So we said that if the p-value was less than alpha, so in our case 5%, then we would reject the null hypothesis. So this is the category that we fall into. So the p-value is less than alpha, so 0.18% is definitely less than 5%. So that means that we can reject our null hypothesis. And in this case, since we were looking at the volume inside these bottles, what that means is that we have sufficient evidence from taking that sample that volume in bottles has changed from before they made changes to the machine in terms of, its filling quality. So that's pretty much all there is for this video, and I'll see you in another one.